We've talked about the atmosphere of Venus. Let's talk about the surface of Venus. The problem is that unlike the other planets, we cannot see directly the surface of Venus. From Earth, telescopes don't help us. Remember, we had trouble seeing the surface of Mercury from Earth because it's always so close to the sun. But Venus gets farther from the sun. We ought to be able to see Venus. Mars, we can see the surface of Mars. You see the surface of the moon. The problem is that those clouds completely block the surface view, even from orbit. Because remember, Mercury, we no problem. We send a spacecraft to Mercury, we can see Mercury up close. If we send a spacecraft to Venus, we see the clouds up close. And so it's really hard to figure out what the surface of Venus is like. Radar measurements helped. And so the early studies, such as Pioneer Venus and Venera, basically used radar altimeters. So as they flew over the surface, then they were able to just figure out how high above they were above the surface. And so if the orbit was circular, but the distance to the surface got less, that meant that, oh, wait, the surface was sticking up more. If this distance got bigger, that means the surface was sticking down some. So that lets you figure out where the high and low regions were. And you can make sort of maps here, and they found that there were like 2 or 3 really high regions and 2 or 3 lower regions. Okay. The best maps came, though, in the 1990s, and that was the Magellan spacecraft. And so the Magellan spacecraft orbited using another type of radar, side imaging radar. This is the sort of side imaging sonar that was used to find the Titanic and several other shipwrecks. That instead of just going straight down and up, you kind of go at an angle, and then the signal bounces back to you, and so it allows you to see profile or relief a little bit better. And so this measured the surface, but it reflected off the surface in such a way that you could actually tell more about it. For example, if the reflection went off in that direction, it tells you the surface is smooth, but reflected back to you, that meant that the surface was kind of rough. And so they could figure out not just how the elevation of the surface, they could figure out how rough or smooth it was. So that led rise to a new set of maps. And so we have several different maps right here. And so we have a couple of regions here that stick up kind of like continents would stick up. Now, this is not like continents on Earth, where continents are made of clearly lighter colored rocks and so forth, granites and things. Here, it turns out that those are basalts. So those are actually what would normally be ocean floor stuff. Those continents are really probably volcanic features, kind of like the Hawaiian Islands or hotspot volcanoes. This is not at all continents like on Earth. There's no ocean floors. There's no evidence of rifting. There's no evidence of subduction zones. There's no evidence of plate tectonics at all here. And so what we find is that all we have are a few mountainous sort of regions here, things that stick up a little bit, and then most of the rest of it is like rolling plains that have little bubbles and ripples in them. Okay, all the features are named after women. So Venus, goddess in mythology, and so the idea was that all the features named after women. So the big continent-looking thing there is called Ishtar Terra, Ishtar, a goddess in mythology. All the other mountains are named after women. Craters they found are named after women scientists. That's a convention. The only exception to that is a mountain range that was discovered with the Arecibo telescope, bouncing radar images off of Venus rather. That was the very first thing they found, and so they named it after James Clerk Maxwell, who came up with Maxwell's laws and the basic idea of light. And so those are called Maxwell Monts, or the Maxwell Mountains. Everything else is named after women. Almost 80% of the surface is volcanic plains with rolling hills, what we call wrinkle ridges. The two continent-looking things, Ishtar Terra and Aphrodite Terra, are probably basaltic flows, kind of like the Hawaiian Islands, not granites like continents on Earth. So my slide here, I put continent in quotation marks because they're not really continents. There's a whole bunch of other volcanic features, many big round sort of things with radial features called Coronae or Arachnoids, and they're basically two variants of the same sort of thing. Volcanic features dominate. You're not going to have subduction zones or that kind of stuff, so you don't have anything bringing metamorphic rocks up. You don't have plates shifting and cracking and so forth. You also are not going to have rain, water, very little wind, so that means sedimentary features are negligible. So volcanic stuff dominates. And it's so hot that lava will actually stay molten for a very long time. It doesn't cool off as quick. And so there are volcanic rivers on Venus that are almost as long as the River Nile on Earth. So these are massive, long volcanic rivers. And then we have, so that's a volcanic river over here. We have a volcano here with giant lava flows coming out. We have a volcanic crater here, and then big fields of wrinkly sort of stuff. The wrinkly stuff tends to be brighter in these images because of the way it reflects the radar. This would be a corona right here, another corona on the right, and these are basically places where the lava was coming up from below, and it kind of cracked the surface, and so you crack the surface here as you push up the ground, and so that's what's going on here. Those are cracks on the surface right there. Okay, and so these sort of roughly circular sort of things called coronae, and if you have lava that starts coming out from the middle, crossing all those things, it looks almost like a spider web, and so those are called arachnoids. There's a couple weird looking things here. Farra, which would be pancakes, and so what we have here is probably the best guess might be there's some kind of subterranean fault and lava is working up along there, and so you get these sort of a line of volcanoes across there. And they're kind of like flat top volcanic features, again like pancakes. The lava comes up, spreads out really fast, it doesn't solidify very rapidly. And so, so you get these sort of round pancake looking volcanoes. Everything that's solid in the solar system has been hit by something. So even though Venus has this really thick atmosphere, the iron-rich meteorites will punch right through, and you'll get an impact crater. And so these are examples of impact craters right here. And so what we notice is that it's smooth and therefore dark in the middle, and then rough on the outside through all the material, all the ejecta. And so those are impact craters. Most of the surface of Venus seems to have roughly the same number of craters. So in other words, not like one part has more craters than the other, suggesting that the surface of Venus is pretty much uniform in age. Now this has got a lot of questions. What does that mean? You know, the entire surface is pretty much the same age. One speculation means that suggests that maybe that heat builds up and the entire surface melts and then it resolidifies, and then after a while melts and resolidifies. The other idea might be that you have planet-wide volcanic activity that resurfaces the area at roughly the same rate everywhere. And so they're still trying to work out the details between those two different models. They don't really know why, but it does appear that pretty much the entire surface of Venus is uniform in age. The faults and fissures and cracks, this is not due to plate tectonics. This is not due to rifting or anything like that. There's no subduction events. There's no splitting here. The cracks are mostly, the faults are probably due to volcanic features, that the ground is uplifting and subsiding due to volcanic activity, and that cracks the ground, and so you get faults. Venus and Earth are about the same size, so Venus should have a conductive mantle just like Earth. Now on Earth, that conductive mantle gives rise to plate tectonics. You get rifting and continents and oceans. On Venus, that doesn't happen for several reasons. One is it's too hot. On Earth, you can have different kinds of rocks, light rocks and heavy rocks, and so the heavy rocks can ride up under the light rocks. On Venus, it's so hot, you actually bake the rocks and you release carbonates out of the rock. That actually makes the rocks denser and heavier. That means you don't get the kind of lighter kind of rocks you have on Earth, and so you don't get that subduction possible. The problem here is that Venus actually has a thicker crust than Earth, so it's very much harder to actually make it move around. So it's really hard to get plates to crack and move because the crust is thicker. And so you got to get the heat out somehow. So what happens is that on Venus, the big convection tends to break up into smaller convection, and it crumples the surface. So rather than moving big chunks of the surface around back and forth, it crumples the surface and makes these like wrinkles and ridges and rolling hills all over the place. And so that's what's going on. So then what happens is you end up with volcanic activity here and there, and so you end up with volcanic mountains all over the place, and then when you try to move anything, just piles of stuff right there. But it doesn't actually make continents. Okay, so this is not plate tectonics, so what would you call that? Well, some geologists call it flake tectonics to indicate that it's something quite a bit different. So again, Venus and Earth, you know, the interior is probably very similar. They're about the same size. They have about the same mass. They probably have roughly the same size core, roughly the same mantle. Venus has a thicker crust. Earth's crust is thinner, and you have the light crust and the heavy crust, the thin crust and thick crust. And so what that means is that on Earth, you can get plate tectonics. This is a big deal because it changes the kind of volcanic activity that the planet has. That means that the volcanism on Earth and Venus are quite different. The volcanoes on Venus are much more like the Hawaiian Island volcanoes. These are much more like hotspot volcanoes, which actually produces more of the sulfur and phosphorus into the atmosphere. And so that changes the nature of the atmosphere because the crust is different. So the question is, are there active volcanoes on Venus right now? Earth has active volcanoes. The moon does not. Mercury does not. We have no reason to suspect active volcanoes on Mars either. But what about Venus? Well, one thing we do know is that Maxwell-Montes is too tall. That under the temperature of Venus, the rocks should get soft enough that those mountains would sink under their own weight. So something keeps pushing them up. That has to be coming from below. That would be volcanic. Now, we do know that the kind of volcanism we get here can produce a lot of sulfur dioxide. And as different spacecraft were orbiting Venus, they noticed that the sulfur dioxide was different when different spacecraft visited. Venus Express actually, as it was orbiting, did monitor that the amount of sulfur dioxide changed while the spacecraft was there. It was getting lower, 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 then suddenly much bigger, then lower, 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 then bigger. That's what you'd expect if you had volcanic eruptions now and then. They also noticed that the surface characteristics changed slightly on Venus. So that, again, that would suggest that we would have volcanic activity. So on Earth, a lot of these volcanic gases get pulled into the ocean and subducted. On Venus, they either go down to the surface or into the atmosphere. And so that makes the surface of Venus, you know, all these gases spewing out. The surface is actually very, very difficult here to explain. And it becomes much easier to explain if we assume that, in fact, we have active volcanism.